Hello dear students, and you are welcome to the third secondary physics program. Today's lesson is very important. Do you know why? Because I am going to make a revision on the standing waves and the general law of the vibrating of strings. Get your pen and paper, concentrate well, and try to answer all kinds of questions. Let's get problems on standing waves. We need first to know what is meant by the standing waves. It is the superposition of two identical waves having the same frequency and amplitude, but traveling in opposite directions to form nodes and antinodes. Here, we want to know what is meant by nodes and antinodes. Node, it is the position at which the amplitude vanishes. That's to say, particles at rest. Antinode, it is the position at which the amplitude is maximum. What about segment? Segment is a part of the standing waves between two successive nodes. It has one antinode, also its length equals lambda over 2. The wavelength of the standing waves. It is twice the distance between two successive nodes or two successive antinodes. Now it's time to have a problem. The first one, a vibrator of 50 Hz is used to produce standing waves. The distance between two successive antinodes is 47 centimeters. Find the velocity of waves. The solution. The data of the problem is the frequency equals 50 Hz and the distance equals 40 centimeters. We have to change it to meter divided 100. It equals 0.47 meters. We need to determine V. Since V, the velocity, equal nu times the wavelength, therefore V equal 50 times the wavelength. But we don't have lambda. He said in the problem that the distance between two successive antinodes equal 47 centimeters. That represents what? Good. That represents half lambda. Since D equals half lambda, from which 0.47 equal half lambda, therefore lambda equals 0.94 meters. So it is easy to substitute in the relation. Therefore V equals 50 times 0.49. It equals 47 meters per second. Another one. A string of a length 2 meters. It has a mass equal to times 10 to the power negative 3 kilogram. Is stretched with a mass of 20 kilogram. Find its fundamental frequency and the second overtone. If the acceleration g, free fall acceleration, equals 9.8 meters per second squared. The solution. We need first to determine the mass per unit length. Since m equals m, the mass of the whole string over the length of the string, it equals 2 times 10 to the power negative 3 over the length of the string 2. Therefore, m equals 10 to the power negative 3 kilogram per meter. Since nu equals n over 2L root ft over m, therefore nu equals n, here the fundamental tone we substituted by 1 over 2 times the length of the string 2 root ft. Here the mass stretched with a mass 20 kilogram. We have to multiply it by 9.8 to change it to Newton. over the mass per unit length 10 to the power negative 3. We get 110.67 Hertz. Second, to get the frequency of the second overtone, that's to say, the number of segments here, how many? Good, 3. Therefore, we substitute in the relation nu equal 3 over 2 times 2 root 20 times 9.8 over 10 to the power negative 3. We get 332.039 Hertz. Or we can get it by another way. Since nu1 to nu2 to nu3 at the ratio 1 to 2 to 3, to get the second overtone or the third harmonic, we have to multiply the fundamental tone by 3 to give the same number, 332.0939 Hertz. Good. Here we have give reason for. The fundamental tone has the smallest frequency. The fundamental tone has the smallest frequency. We all know that nu equals n over 2L root ft over m. From this relation, it is clear that the relation between nu and n is directly proportional. Since the fundamental tone has the smallest number of segments, therefore, the fundamental tone has the smallest frequency. Second one, give reason for. The thin string emits sharp tones, while thick one emits thick tones. Do you know the answer? Since nu equals n over 2L root ft over m, from this relation, it is clear that the frequency nu is inversely proportional with the root m, the mass per unit length. Since mass per unit length equals rho times v, rho density times v, from which the mass per unit length equals pi r square law. Therefore, nu is varies with 1 over root pi r square rho. That's to say, by decreasing r, nu increased. Another kind of question. Choose the correct answer. If the tension force is increased 4 times its value, then the velocity of propagation of waves increases double, decreases double, stay constant. Which one? Good. The answer is increases double, as V equals root Ft over m. When the tension force increases 4 times, then the velocity increases double. Another one. If the length of the string is doubled, so the frequency of the emitted tone will be increases 3 times, increases twice, decreases to half, at constant Ft and m. If the length of the vibrating string is doubled, so the frequency of the emitted tone will be increases 3 times, increases twice, decreases to half, at constant Ft and m. Which one? The answer is decrease to half. Since nu equals n over 2L root Ft over m, as we said before, it is clear that nu is inversely proportional with the length of the string. In Mills experiments, the length of the string is 2.5 meter. If the wavelength is 0.5 meter, find the type of the emitted tone and the number of nodes and antinodes formed. The idea of this problem is to find the number of segments. Since L equals 2.5 meter, lambda equals 0.5 meter. We all know that L, the length of the string, equals N times half lambda. L equals 2.5 equal N times half lambda here 0.5. Therefore, 2 times 2.5 equal 0.5 N, from which we can get N equals 2 times 2.5 over 0.5, it equals 10. Therefore, the string emits the 10th harmonic or 9th overtone. Since the number of antinodes equal the number of segments, that's to say equal 10. But the number of nodes equal the number of antinodes plus 1. Therefore, the number of nodes equal 10 plus 1 equals 11 nodes. Another one. A string vibrates emitting its fundamental tone according to the relation nu equals 150 over L. Find the velocity of transverse wave in a string. The solution. Since nu equals n over 2L root ft over m, since the tone is the fundamental tone, therefore the number of segments equal what? Good, equal 1. Therefore nu equals 1 over 2L root ft over m. But root ft over m is equivalent to the velocity of the wave. Therefore, nu equal 1 over 2L times v. Since nu equal 1 over 2L times v, but from the problem he said that nu equals 150 over L. From these two equations, it is clear that v over 2L equals 150 over L. We can cancel L from both sides of the equation. Therefore, V equals 300 meters per second. The last one. In milled experiments, an electrically maintained tuning fork of a constant frequency is used when a load of volume V and density 2,500 kg per meter cube is hanged at the end of the string. The string is divided into 4 segments. When the load is totally immersed in a liquid, the string is divided into 5 segments. Find number 1, the ratio of the tension acting on a string in the 2 cases. The second one, the density of the liquid. The solution. Since nu equals n over 2L root ft over m, therefore nu1 equals 4 over 2L root ft1 over m. What about nu2? Nu2 equals 5 over 2L root ft2 over m. Since nu is constant, therefore 4 over 2L root ft1 over m equals 5 over 2L root ft2 over m. We can cancel math the per unit length from the 2 equations and the length of the string. Therefore we get 4 root ft1 equals 5 root ft2. Therefore ft1 over ft2 equals what? 25 over 16. This is the first required. What about the second one? To get the rho of the liquid, since T1 in the first case equals the weight of the body, as it is in air, but in the second case when it immersed in a liquid, T2 equals the weight of the body minus the buoyant force. Therefore, T1 over T2 equals